In the blockchain industry, specifically in the DeFi space, there have been a ton of exploits, hacks, and vulnerabilities that have led to millions of dollars being stolen and exploited out of smart contracts. A lot of these issues tend to happen from poorly written smart contracts not following the proper protocols or best practices. In today's tutorial, we're going to be going over the mishandling of exceptions and access controls. My name is Anthony. I'm with the Blockchain Dojo, where we turn you into a blockchain ninja and a Solidity expert. If you like what you watch, please like and subscribe for more content. Let's get started. First, we're going to go over what a mishandled exception is. So ultimately what a mishandled exception is when the developer doesn't properly check for return values or throws an exception where it isn't supposed to be thrown. Essentially just a weakness or vulnerability or a bug in an exception clause or a return value that isn't checked. Typically, when you do not check return values, you're not actually checking if the function calls return the proper values and actually checks required. So mishandling these exceptions and mishandling these checks can lead to vulnerabilities, such as making a function call to transfer funds out while the remainder of the function is dependent on the success of that transaction without actually checking if the transaction is successful or failed. Very easily execute a function where you make an external contract call that ultimately fails, but your contract doesn't take that into consideration and still executes the rest of the function instead of reverting it, ultimately leading to an exploit or weakness, vulnerability, or potentially be a siphoning of funds. The mishandling exceptions vulnerability happens right here in this code under the payable message.sender.transfer/refund. There's actually a second vulnerability here in this code piece. I'll pause the video now and comment below if you can identify it before we go over what it actually is. But back to it, the mishandled exception right here is the unchecked return value of payable message.sender.transfer/refund, as this ultimately updates the state variable to 0 regardless on whether or not the transaction is successful or fails. So to mitigate this vulnerability, what we need to do is actually the syntax of bool, comma, and then space, as this payable message.sender transfer actually returns two values, which is a Boolean on whether the transaction was successful as well as the bytes of data, but we can ignore the data bytes. Second, what this does is this stores the return value of success or failure in the bool sent, and then right underneath that we just require that sent to be positive or true, So essentially what this means is that if the transaction fails and this require sent statement is triggered, the whole function will revert, essentially never updating these contributions of message.sender to 0, meaning that the message.sender can still actually withdraw their funds or their refund. Now, the second vulnerability on this contract, and we went over this in a previous video, but there is actually a reentrancy vulnerability here. Under contributions of message.sender equals 0, this actually should be pushed above the mishandled exception. That way the state variable is updated. So when these funds hit, let's say, a malicious contract that calls back into our withdrawal contribution function, the state variable is already updated, meaning they can't call back into the function and withdraw more funds than they actually have available. The next vulnerability we're going to be going over is going to be unauthorized access. For my software engineers that are familiar with the principle of least access, this essentially is that limiting access to functions only being called by the appropriate party, meaning the admin, the owner, or a manager. There are other ways that you can actually set up roles that allow other users to call these functions, but ultimately access control is just limiting the ability to access certain functions or key functionality within a smart contract. So this is an example of the unauthorized access vulnerability. As we can see here in the function withdrawal contract, that this function, which does follow the proper mishandled exceptions, where it's bool success equals message.sender.callValue, address this dot balance. So while this does follow the proper checks and requires statements to ensure that the transaction passed, what this does not check is it does not check that the caller of this function is actually the owner of the contract, meaning anyone can come in here and call this contract and have the entire value or balance of this contract transferred to their own wallet. All of you can understand how drastic and how bad that type of vulnerability could be, where an entire contract's funds can be transferred out without any issues. Thankfully, this vulnerability is a very easy one to mitigate. And this is actually a principle that you should keep in mind when you're writing any smart contract that requires any type of access controls. Always include your require message.sender to be equal to owner require statement. That way, if someone who is unauthorized calls your contract or calls your function, the function's reverted and there's no actual damage done. There's other ways that you can include this require statement, such as using like an only owner modifier, which is something that I use quite frequently. But ultimately, the require message.sender equals owner is a great way to mitigate this vulnerability. Thank you to everyone who stayed to the end. Really appreciate it, and I hope you guys learned something new today. In this video, as I mentioned, we went over mishandled exceptions and unauthorized access vulnerabilities and how to mitigate them. If you learned something new, please like and subscribe, and stay tuned for more content.